So in this next video, we're going to look at one more example of how you actually compute the moment of a force using a scalar formulation. And if you were given here kind of an L bracket that's fastened to a wall at point O, we're told that the kind of horizontal dimension of this L bracket is 5 meters. And I'm drawing it as I talk. I'll eventually switch to my dot cam. The vertical dimension of this L bracket is 2 meters. And we're given some specific kind of locations of the geometry. If you notice, they've conveniently defined this 5 meters as being kind of the distance from the wall to the point of application of that force. So we're kind of still using hand waving and particle assumptions, but that is okay. And we're applying a 100 Newton force, and we're given some geometrical information that will allow us to do the decomposition. What we want to do is find the actual moment of that force about O of the 100 Newton force. So let's actually talk about how we would go about doing this. So just like the example that I spoke of earlier, the easiest way to do it is going to be to actually decompose that 100 Newton force into components. So I'm going to say step 1, I will decompose the 100 Newton force into components. And the reason that I'm doing that is if I had it into individual components, it would be very easy for me to compute the perpendicular distances that I need, and in addition, actually compute the corresponding sense of the rotation of each. So what I'm going to do, if you go back and look at the actual slide that you're given, you're told that it is similar. The force triangle that you would get is similar to a geometrical triangle that has a hypotenuse of 5 and actual vertical distance, and I want to make sure that I'm using some nice pen colors here, of 3, so Fy here, and a horizontal distance of 4. So I will just write that up here, the 3, 4, 5 triangle. So I'm sure everyone has seen like the trick, now that you've done enough of these, of how you actually decompose that force given that information, but I'm going to do it the long way just one more time to show you. So what we would need in order to do the decomposition is an interior angle of this triangle like here, which is theta. And what we know is that if this geometrical triangle is similar to this force triangle, then these two angles are the same thing. So I don't actually need to solve for what theta is. I can more easily find what the cos of theta and the sine of theta is. So notice that the cos of theta is going to be the adjacent side length divided by the hypotenuse, which is just going to be 4/5. The sine of theta will be 3/5. So what that means is that when I actually do this decomposition, I can write Fy in terms of the hypotenuse, 100 newtons in the force triangle, times, notice that this is opposite the angle that we're given. So it's going to be related to the sine of theta. So if you do 100 times 3/5, what is that going to be? 60. And that will actually be in newtons. Now the question is, do I need to do a sign convention? Well, I'm going to put it in here for now because according to everything that we've done so far, this is in the negative y direction, so I should track it that way. What would Fx be? Well, it'll just be 100 times cos theta. And notice that cos theta was 4/5 here, and it's going in the positive direction, so I won't actually need a correction. So that will be 80 newtons. So if I were to actually decompose this force into x and y components, it would have an x component of 80 and a y component of minus 60. But what we're going to see here in a minute is oftentimes when you do these moment problems, you kind of ignore the signs and you just work with them as magnitudes. So we have done that decomposition. So now the next thing that I'm going to do is compute the actual moment about point O of each component. And let's actually start with the y component. So remember that the way that we're going to do that is we're going to draw in the line of action of our force, and we're going to ask ourselves what the perpendicular distance is. So notice that for that vertical force, the perpendicular distance is 5 meters. So I will say d perpendicular is 5 meters. There's a ton of lines you can draw from the origin, but the only one that actually will form a perpendicular is going to be 5 meters long. And in addition, the actual sense of rotation, if I pin at O, and I actually pull this down, it's going to be in the clockwise direction. So it's going to be clockwise, which means that we're going to have a sign, a negative sign, to track the actual direction of that rotation. So when I talk about the moment of this force, put in the actual negative. What's the perpendicular distance? It's actually 5. Now here's a little bit of a confusing part. Since I've already accounted for the fact that this y force is going in the downward direction when I computed this actual sign, I'm just going to put the actual magnitude of the force here. So again, the reason that I'm doing that is in a scalar formulation, you kind of determine the sense of rotation by doing that analysis that I already did. So this will actually come out to be minus 300. What are going to be the units of that? That is in meters, that is in newtons. So I would say that's in Newton meters. Now, what about the x component of the actual moment? I should say, what is the moment about 0.0 of the x component? So for the actual x component, if you actually drew its line of action, it's going to be vertical here. Hopefully everyone sees that. So if you were to draw the perpendicular distance, it's going to go right through the formula that I had. I should have thought about that. Notice that that actually forms a right angle versus any other line that I drew would not form a right angle. And that distance that I'm actually trying to report out is 2 meters. And at least when you're working the first few problems in this chapter, the perpendicular distance is usually going to be some dimension of the actual body that you're given. So d perp is 2 meters. What about the actual direction of the rotation here? Well, if you hold this, pin it out, and actually pull it to the right, you'll notice that you're going to get a clockwise rotation. So that is going to be clockwise, which is going to be negative by convention. Counterclockwise is positive. So the moment of this force is going to be the minus from that sign analysis that we did, the perpendicular distance, which is 2 meters, times the actual magnitude of the x component, which is 80, and that's going to be a minus 160 Newton meters. So the total, so for the final step, we would just add the moments together. That's kind of a linearity of forces that we've done quite a bit so far. Now notice that you have to add them with their signs, but since both of these have the actual same sign, the resulting total moment that that force induces would be 300 plus 160, which is going to be 460 Newton meters. What you'll find is your text often has a convention to write this as 460 Newton meters. And since remember that that negative corresponds to clockwise rotation, they'll actually draw in arrow that actually looks like that to show the actual direction of rotation. So hopefully that made sense, and hopefully you can kind of work through and see why this problem works out the way that it did. Notice that clearly the y component of that force is going to induce a larger rotation because that perpendicular distance is much longer. If you're thinking about if you want to break this thing away from point O, eventually we're going to do equilibrium analysis. If you want to break this off from point O, you would push down a lot harder than you would ever pull out that way because that has the big perpendicular kind of lever arm to it. So that's why in this calculation, notice that this perpendicular distance was larger. So even though that component of the force in the y direction was a little bit smaller than the x component, it contributed a larger amount to the actual moment about 0.0. So I'll see you in the next video, and we won't be doing actual scalar formulations to moments anymore. We'll do vector formulation.